Unit 2 is about atoms, molecules, and ions. So we're going to look at how the atom was developed as far as our model, and then how molecules and ions exist, and we will review how to name compounds in class. So the early history of chemistry, first you had the Greeks like Democritus thought that matter was made up of 4 substances: earth, wind, fire, and water, and they practiced alchemy, where they were trying to convert things into other substances. Democritus was a philosopher who said that matter was composed of small particles called atomos, which is where we get our word atom from. So before the 16th century, alchemy was practiced, again changing substances into another substance. Taking elements and trying to make gold is one of the big points of alchemy. In the 17th century and on, chemistry was practiced, and that's because of Robert Boyle. You might remember him from Boyle's Law in Chem 1. He was the first quote-unquote chemist to perform quantitative experiments. So alchemy didn't really have, or chemistry before this point didn't really have numerical data to back up what the theories were. And then from the 17th century on, we developed those techniques. There are 3 chemical laws that we have to follow because that's what chemistry is based on and how our substances interact. The first one is the law of conservation of mass. Antoine Lefebvre, I can't say his last name, was a French chemist. Anyways, he was the father of is considered the father of chemistry. He said that mass is neither created nor destroyed, but they're equal. So whatever the mass that you start with has to equal the mass that you end with. So what happens when we burn something? Because if we burn a log, we don't end up with the same weight as the log. Well, what happens is some of the mass turns into a gas, and so it escapes if it's not done in a sealed container. So if it seems like some of our mass is disappearing and that our masses aren't equal, that's probably because we formed a gas, which then escaped into the atmosphere and we didn't connect it. The law of definite proportions says that you can't have part of an atom, it's all of the atom or nothing, so the ratios in our compounds are always whole numbers. The law of multiple proportions says that you can take any 2 elements, so like carbon and hydrogen, organic chemistry here, and you can form a series of compounds. So you have CH2, CH4, C2H2, C3H8. They're the same elements but in different ratios, and those ratios based on the definite proportions should always be whole numbers. Dalton's atomic theory says that matter is made of tiny particles called atoms. We still believe that today. Atoms of one element are identical. Atoms of different elements are different. Well, we don't really believe the identical part anymore, and that's because of isotopes. So you can have atoms of the same element with different masses, so they're not identical. Atoms can be rearranged in chemical reactions. We believe that. Compounds have to be whole number ratios. We believe that. Atoms cannot be subdivided, created, or destroyed. So subdivided, we now know we can subdivide atoms, and that's called fission. Now, AP Chemistry assumes you remember your nuclear chemistry from Chem 1. So if you don't, you need to go back and review it. So atoms can't be created, and you can't destroy an atom into nothing. You can't create an atom from nothing, but you can take an atom and subdivide it or split it into different things, which is what fission is. Avogadro's hypothesis, and yes, that's the same Avogadro as Avogadro's number. He said that at the same temperature and pressure, equal volumes of gas contain the same number of particles. And this is from the ideal gas law. So PV equals nRT, or PIV-NERT. If T and P are identical, then at the same volume, you're going to have the same number of moles. It doesn't matter the gas. If you have the same number of moles, then you have the same number of particles, atoms, ions. The masses don't have to be equal, but the amounts of moles and particles and molecules would be the same. Okay, so the atom itself. You need to be able to tell the history of the atom, including major experiments and the progression of the model. So first we have Thomson's cathode ray tube, which led to the plum pudding. So you have this tube of gas, and it's called the cathode ray because we have a positive end, which we call the cathode, and the negative end, which is called the anode. What he saw when he hooked up this electricity was that the gas inside the tube was kind of attracted to the positive end. It would swoop away from the negative. He also did things like put little windmill type things or propellers in the middle of it and see what happens if the gas would make it spin. He put magnets around to see if he could get the gas to go to the top of the tube or the bottom of the tube. And from that he discovered the electron. So our atom, he called it the plum pudding model. You have positive substance and you have these negative things which he called the electron in. So it's important that you know the negative electron. The electron is negative. And then he figured if there's something negative, it's got to be something positive. So we come up with the plum pudding. Millikan also looked at the electron, but what he found was the mass of the electron. So he did an experiment called the oil drop experiment, and he sprayed some oil in. Again, you have this positive and negative fields, and the X-rays produce charges on the oil drops, and from his data he was able to determine the electron's mass is very, very small. In fact, it's so small that in class we're going to say that the electron has no mass. But in reality it does. It's just really small compared to the rest of the atom. Based on those, we're kind of in line with the oil drop experiment. Wilhelm Roton noticed that the cathode rays cause things to give off unusual rays, and these rays could not be deflected by a magnet, so they didn't contain a charge. He called them X-rays. X because he didn't know what they were. Becquerel noticed that there was also rays spontaneously coming off uranium compounds, and he had wrapped these uranium compounds, or he took photo paper and kind of wrapped it in there around the paper, and that he had these spontaneous rays coming off. They differed from the X-rays because they would occur on their own, where the X-rays you had to hit it with the cathode ray, or it had to be in a cathode ray to see them. Well, Marie Curie actually worked with Antoine and suggested that the name should be radioactive, that uranium would be radioactive, to describe his observations of these spontaneous rays coming off of the uranium compounds. So all of this leads to three types of rays produced from a decay. You have alpha, beta, and gamma. Alpha is a positively charged particle. It actually, when the nucleus decays, it turns into one of the products it can give off is a helium atom, which is what the alpha particle is. The beta is just an electron. And then you have gamma, which is energy. And since it's purely energy, it doesn't have a charge. So if you think about a radioactive sample, uranium, and you're firing its rays coming off through a field where you have positive and negative, what you would notice is that the beta particles, which are negatively charged, get attracted to the positive side. The alpha particles, which are positively charged, are attracted to the negative side. And that gamma would simply pass straight through unaffected because it doesn't have a charge. Also notice the bend in the beta and alpha. Notice that the alpha is slower to fall down, and the beta happens pretty quickly. The beta is moving at a much faster speed because it doesn't have any mass, where alpha goes very slowly because it's considered heavy. I know 4 doesn't seem heavy, but it is. Back to our atom. Rutherford's gold foil experiment showed us that the atom is mostly empty space, but there is a small dense area of positive charge. We now call that the nucleus. So we had to change from our plum pudding model to this planetary model where we had that clump of protons and neutrons in the middle and our electrons are orbiting around the outside. Our modern view of the atom says that electrons are found in the electron cloud. They have a negative charge and zero mass. They do not circle the nucleus. They're contained in the electron cloud, which is three-dimensional orbitals, your S, P, D, and F, and hopefully that rings a bell to you. Protons are found in the nucleus. They're positively charged. They have an equal charge but opposite charge to the electron, so that one electron and one proton cancel each other's charges. It has a mass of 1 AMU though, where the electron we say is 0. The neutron is found in the nucleus. It has the same mass as the proton, 1, but it doesn't have a charge, so it's neutral. So isotopes, we have this shorthand isotopic symbol, A over Z, X, and then a spot for the charge. So A represents mass number. Z represents the atomic number. Because Z is the atomic number, it's not always given to us. And then where this yellow box is would be your charge. Those are your 3 points on your isotopic symbols. So if we look at the example of sodium, sodium has a mass number of 23, and it has an atomic number of 11, and it has a charge of +1. Now it's important to remember that mass number is equal to protons plus neutrons. Mass number is specific for an atom, where the molar mass or average atomic mass is specific to an element, which would include all of the different types of isotopes for that element. So this specific atom of sodium has a mass number of 23. The atomic number, if you remember from Chem 1, is the number of protons. So for this isotope, I have 11 protons. For neutrons, I would say 23 minus 11, so I have 12. And then the electrons, if this was neutral, if I didn't have anything in the upper right-hand corner, then I would have 11 electrons. However, I have this positive charge, which means I have to have one more proton than electrons. So I actually have 10 electrons. Remember, you cannot change the number of protons. That has to remain the same. All right, another example. Hydrogen actually has 3 isotopes. You have the traditional hydrogen, you have a deuterium and tritium isotopes for hydrogen. So what's the difference? Well, it's hydrogen, so they all have a proton. There's no charge, so they all have 1 electron. So the difference comes down to the neutrons. Here we have a mass of 1, so we don't have any neutrons. Here we have a mass of 2, so we have 1 neutron, and then a mass of 3 means I would have 2 neutrons. Different isotopes can have different properties. So if we look at the 2 isotopes that are most common for uranium, we have uranium-235 and uranium-238. The uranium-235 is the one that is radioactive. It's the one used in the atomic bomb. It's the one used in nuclear reactors. It's the one that they worried about in Japan with the Fukushima meltdown when the tsunami and earthquake hit. However, uranium-238 lacks the properties for nuclear applications, so it's more stable than uranium-235.